So your video on concave mirrors ended up being quite long. This one I'm hoping to keep pretty short, maybe even the shortest one ever. We'll see how it goes. So jumping right in, just like before when we had our concave mirrors, we started looking at what happens to parallel rays that are incident on the mirror. So here we've got a parallel rays again. Remember, these come from a distant object or from the sun or something like that. And when these rays hit, instead of being focused to a point like they were with the concave mirror, they're actually scattered out. But that's okay because our eye can make images from the scary looking eye. But anyway, it can make images from diverging rays. That's exactly what we need to make an image, in fact. And even though the rays didn't come from a focal point, our eyes are able to focus them, and it seems like they did. Our brain kind of extrapolates backwards and says, well, if this line is going straight and light rays always travel in straight lines, it must have come from this location here, which we again call the focal point, and the distance between the mirror to the focal point is still called the focal length. And the focal length is still half the radius of curvature, so we have the same equation here where f equals 1/2 times r. Okay, now if we think about rays that are coming off an object that's nearer to the mirror instead of far away and having parallel rays, we can follow similar principles to what we did before to draw our ray diagrams. A light ray that is initially parallel will reflect off, but when we extrapolate back, that goes through, it appears like it came from the focal point. Okay, one that goes straight at the mirror, perpendicular to it, perpendicular to the surface at that location, that one will bounce straight back, and that will appear to have come through the radius of curvature. We can draw a third one as well that bounces off the middle here. I'll give it a try. It's probably not going to turn out well, but there you go. So that one is bouncing off, coming this way, went that way. So that appears like it also came from this same point here. So this is where our image location will be. As it mentions here, for convex mirrors, they're kind of easier than concave mirrors because there's only one thing that ever happens. There are always virtual images, which remember means they're behind the mirror where the rays didn't actually go, but they our mind kind of interprets them as having come from there. But if we put a screen behind the mirror, there will be nothing on the screen because no light rays actually went there. They will always be upright, and they will always be smaller than the object. We use the exact same equation, the mirror equation, to analyze convex mirrors. We just have to be careful with our sign conventions. So we have 1 over di plus 1 over do equals 1 over f. Everything is identical. For convex mirrors, though, f is now going to have a negative sign on it. For concave, before they were always positive focal lengths. And because the image is behind the mirror, the image distances are always going to be negative. Object distances, we're pretty much always going to have positive, except when we have more than one lens going on, but we'll get to that at some other time. Okay, so we have similar things going on. And these mirrors, as far as the functionality of them, sometimes it's really useful to have things shrunken down because that gives you a wider field of view. So these are used like for side view mirrors, even though it's not too drastic. They are somewhat curved. They're somewhat convex, so you get a wider field of view. And you might have seen on some of it says that the objects are smaller than or closer than they appear. And really, that doesn't have to do with the image distance so much as the fact that they appear smaller. And when we see things that are smaller, we interpret them as being farther away. They use these types of mirrors in the corners of convenience stores and stuff, so you can see around the corner and make sure nobody's stealing anything and things like that. Okay, so my summary table, like I had last time, not needed so much for this one, but you can add this to your notes. So this is for convex mirrors. Always the same. With concave, we saw that it depended on whether you were closer or farther than the focal point or radius of curvature. Here, none of that matters. No matter where your object is, we're always going to have positive object image distances, negative image distances, which means they'll be virtual, upright, and they will be smaller, so the magnification will be between 0 and 1. I guess we could add the focal length on these is always going to be negative as well. It's a little addition to our table. Alright, let's look at our little demonstration here. So this one adds a third array. This one, oh no, I already added that one. Never mind, has the same 3 that I had. Alright, so if we move this back and forth, then it doesn't really matter. I mean, it affects the amount of magnification. If you're close up, then it's not shrunken as much. If you're real far, then it gets really small. You will notice that this image here is always closer than the focal point, so you can never get the image beyond that. But the object placement doesn't really matter. If you have it upside down, then they're both inverted, so you'd still say the magnification is positive because a negative means inverted, but we mean inverted compared to the object. So if they're both upside down, that's not an inversion. Alright, that's about it. See you next time.